Hey everyone, in today's video lesson we'll be looking at power and efficiency. Now before we get into any of the formal definitions or mathematical equations, I want to give you kind of the idea of what the end goal here is, and that would be to understand that many of our electrical devices draw energy or draw power, and there is a cost to that. And each month you would pay an energy bill or an electrical bill, and I suppose the end goal is for you to be able to understand what that energy bill is communicating. So that's what I'm hopeful for, and we'll see a little bit more of that towards the end of the video. So let's get started, however, with the concept of what power is. Power is the rate at which an electrical device or devices consumes energy. So every electrical device consumes energy. The power is how much energy it actually uses. And actually that kind of leads us into our formal definition. Now, the unit for power is watts, named after James Watt. And he's a Scottish engineer that came up with the definition for power. And 1 watt is equal to 1 joule per second. Now, that very formally is, well, second is a measurement of time, and a joule is a measurement of energy. So 1 watt is equal to 1 joule per second. So a watt power really is just how much energy used per time. That's kind of what we're getting at here. So let's actually go into how we calculate, and there's, to me, just a few ways to calculate this. Power is equal to energy divided by time. That's actually kind of formally noted here. This is energy divided by time. So that must be a way for us to calculate power. Another way to calculate is power is equal to current multiplied by voltage. So these are the two ways we often calculate power. Let's see an example of using one of these equations. So get rid of that, bring that up. Okay, so my toaster draws 900 watts of power. What is the current consumed by the toaster? So we know that the power is equal to 900 watts, and we actually want to know what the current is. So you guys can maybe copy that question down. We'll go back to here. So I have that the power is equal to 900 watts, and I want to know the current. Well, that means I would have to know the voltage, which I kind of implicitly do. That kind of means I don't have to be told. So let's just set up our equation, and this should become somewhat clear shortly. So 900 is equal to the current that I want to know, multiplied by, well, my toaster is plugged into the electrical outlet, which is a 120 volt outlet. So that's my equation. And so now I can solve this. I can divide both sides by 120. And the current is equal to 900 over 120, which, if we calculate, is 7.5. 7.5 amps. So that is the current that the toaster draws. Now, maybe that doesn't seem like a lot, maybe it does. What you should know is, and this is kind of anecdotal, it's going to be different for every household, but when I was growing up, the circuits could actually only take about 15 amps, so you couldn't kind of run the toaster and the microwave at the same time, because that would kind of blow the fuse. And so it kind of depends on how much the circuit can take, or how much the fuse can take before it breaks, or blows the fuse. So this 7.5 amps is actually, that's a good amount of current. So just kind of keep that in mind, that is actually a substantial amount. A fuse rated at 15 amps would blow if you ran this and something else with a high amperage, like a microwave or a stove, so long as it's connected to the same circuit. So moving on, we would like to look at percent efficiency. Now, percent efficiency is kind of this weird idea, but no electrical device is 100% efficient. And we'll talk about why that is, but the equation for this is the output divided by the input. So the concept being, I'm going to input an amount of energy, but I won't get out exactly how much I input. So it's output divided by input multiplied by 100. And this is so that you have a nice percentage. This multiplied by 100. So let's actually see an example of that. Let's say that the output is 2 joules of energy for every input of 100 joules of energy. So if we actually do this, it's 2 divided by 100 and 0.02, and that would multiply by 100. That would actually cancel everything out. So this, I hope you're seeing, is about 2% efficiency. So what this means is that for whatever electrical device this is, you input 100 joules of energy. 2% of that actually goes to what the electrical device is trying to do. So 2% is used for what you want, essentially, and so 2% used properly, I guess, used properly. And then the other 98% would be referred to as waste. It was not converted into what you needed it to be converted into. So it's not that the other 98 joules disappear. You know, that would violate conservation of energy. It's that those 98 joules in this example very simply were converted into something that they shouldn't have been converted into, or they weren't designed to be converted into. And I mean, I'm kind of leading up to this, but this would actually be the percent of efficiency of an incandescent light bulb. So an incandescent light bulb has a 2% efficiency. Roughly. So the other 98%, well, if you've ever had an incandescent light bulb, you know it heats up quite a bit. So in terms of waste, it's not that it's gone, it's not that it got destroyed, it's that it got turned into something that wasn't designed to. So for a light bulb that's 2% efficient, the other 98% usually goes into something like heat. That's actually, there isn't a lot of other, heat or this. It's for efficiency, it's often that the wasted energy is heat. So that would be an incandescent light bulb. I can say that the efficiencies for some of the newer light bulbs, like LED light bulbs, is also not that great, but it's also not this bad. It's roughly around 15 to 25% in terms of efficiency. So that's power, that's efficiency. Now what we want to talk about is, I'll just say the power bill. And what does that look like? And here's the thing. This depends a lot upon where you are, but essentially what a power company is going to do is they're going to charge you a rate per kilowatt hour. So, for example, a rate could be 0.0739. That would be the amount you get charged per kilowatt hour. So we'll say amount per kilowatt hour. And so kilowatt is a unit, and hours is a measure of time. So it's kind of like they're charging you, how much energy did you use and how long did you use it for. And for every kilowatt hour of energy, you're actually going to pay $0.0739, or that's actually just roughly 7.39 cents. So let's see an example of this. I think it's actually the best to see an example of this. So here is that. So the incandescent light bulb draws 60 watts of power. How much does it cost if you keep the light bulb on 12 hours a day for 1 month? So I'll let you kind of take that in, copy that down, and we'll come back to here and we'll try and solve this problem. So we know that the power rating for an incandescent light bulb is 60 watts. We know that it's 12 hours per day, and usually the power company charges you every month, so for 1 month. And this is kind of how we do this. We want to take the power of 60 watts and we want to convert it into kilowatts. So we divide by 1,000 and we get 0.06. So 0.06 kilowatts is 60 watts. So that's a power rating for our light bulb in kilowatts. Now what we do is we take that and we multiply it by however many hours that light bulb was on for the whole month. So actually we have to do 12 hours per day times maybe the 30 days in a month. So it's 360. So we multiply by 360 hours. This represents the kilowatt hours. So if I do that multiplication, it's 21.6 kilowatt hours. And for every kilowatt hour, I am charged $0.0739 or 7.39 cents. So we'll multiply it by 0.0739. And in the end, I guess we'll call this the cost. The cost for that one light bulb to run 12 hours a day for a whole month is $1.59-ish. Roughly $1.59. Okay, so that is kind of how we calculate the power consumption and the cost for electrical devices. Let's look at another example here. The newer LED light bulbs draw roughly 9 watts of power. How much does it cost if you keep the light bulb on 12 hours a day for 1 month? So we'll come back to paper here, and everything else is the same, but now it's 9 watts. So I'm going to do 9 divided by 1,000 and get 0.009. So now my cost is 0.009 times the 360. And again, this was always here, I just didn't write it. You also multiply by the cost per kilowatt hour. So 0.0739. After I multiply all those things together, 0.09 times 360 times 0.0739, you get that the cost is 0.239, or roughly 24 cents to run that LED light bulb. So this is your kind of standard light bulb, this is the LED, and so it costs quite a bit less to run that light bulb continuously. So our next example actually has to do with percent efficiency. So the percent efficiency of this 9 watt LED that we actually just talked about is roughly 20%. How much energy does it draw if it uses 100 joules of energy? So the percent efficiency is roughly, I'll just say percent efficiency is roughly 20%. So as a decimal number, that is 0.20. And we can set it equal to output divided by input. So if it uses 100 joules of energy, how much does it draw? So we're actually looking for the input here. And we know that the output is 100. So we have 0.20 is equal to 100 over the input. So I solve for input. (100 over 0.2). This will be equal to 500 joules. So that's the percent efficiency of the LED light bulb. I hope that makes sense. It's roughly 10 times more efficient than the incandescent light bulb at 2%. Fun fact, it seems the maximum efficiency of an LED light bulb is around 40%. So you actually physically can't go higher than that. So let's take a look at a couple more examples for power bill, and then that will be all. So a desktop computer has an average power rating of 150 watts. How much does it cost to run the computer for 8 hours each day for roughly 30 days? So our power is 150 watts, and I'm running it for 8 hours for 30 days. 8 hours a day for 30 days. Okay, so we'll assume that the cost is still that 0.0739. See, that changes based on where you live, essentially. It's different for different places. So the cost is going to be, remember, I always take that power rating and divide it by 1,000. So 0.15, that gets the kilowatts, multiplied by 8 hours a day times 30 days. It's 240 hours multiplied by the 0.0739. So the cost will be equal to 0.266. Oh, you can see I didn't quite do that right. That number seemed a little low to me. You can see I put the 0.015 instead of the 0.15. So I should get 2.66. Yeah. 2.66. That's $2.66 each month to run that computer for 8 hours. Okay, so let's take a look at one more example. The Xbox One S has this instant on feature. Many of the consoles used for streaming or gaming have this feature. This cuts down the time it takes for the console to be ready to use significantly. The feature itself draws roughly 13 watts. How much does the instant on cost for each month? So the big key idea is the 13 watts here. So power is 13 watts. We're assuming that it's always on, so 24 hours in a day for 30 days. So 13 divided by 1,000. The cost will be 0.013 multiplied by, well, what's 24 times 30? That's 720 hours within the month, multiplied by the 0.0739. So this instant on feature roughly costs $0.692 dollars each month. On a year basis, we multiply that by 12 months a year, and we'll find that to have this It's roughly $8 per year. Now that's in a region where this is the monthly cost of kilowatt hour, or kilowatt hour cost. That just depends on where you are. It could be higher, could be lower, and this will affect this number. I hope that we are understanding some of the math here, as well as the valuable implication where I find that electricity bill is something that can be quite difficult to understand, that really doesn't have to be. So I hope this helps, and that should be everything you need to know for power and efficiency.